Okay, welcome to my new video. Now I'm going to do one example with this sinusoidal excitation which we discussed in my previous video. So if you didn't watch my previous video, you should watch it. And here, I don't know if you see from the light, here it says example number 6. One phase 120 volts 60 Hz supply is connected to the coil of figure 6. Now we have a magnetic circuit here. We have one coil and it's a one phase. It has an RMS of 120 volts and 60 Hz frequency. This coil has 200 turns. The parameters of the core are as follows. Length of the core, so this mean length, is equal to 100 centimeters. Cross-sectional area of the core is 20 centimeters squared. Relative permeability of the core is 2500. We have to obtain for A, we have to obtain an expression for the flux density in the core, and for B, obtain an expression for the current in the coil. Yes? Okay, so now we have to, for A, we have to calculate or find the expression for the flux density in this core. So you know that the flux and the magnetic flux density, and the magnetic flux density are both in phase. There is no phase shifting between them. So B of T is in phase with flux of this core. So the expression is B maximum times sinus omega t, and the flux is equal to the amplitude sinus omega t. You know that omega is angular velocity and it is equal to 2p times the frequency, and that is equal to 2p times 60 because the frequency is 60 Hz. Now how can we measure this? Well, these things are both in phase. You know that the formula for the flux is equal to B times the area, the magnetic flux density times the area, but also that this is also equal for the flux maximum B maximum, and then you get that the B maximum is equal to the flux maximum divided by the area. So we have the area of the core, it is equal to 20 centimeters squared, but we need the flux maximum, the amplitude of the flux. And how can we measure that? Well, in the previous video we saw that the induced voltage is equal to 4,44 N times frequency times the maximum flux. And then the flux maximum is equal to the induced voltage divided by 4,44 times number of turns times frequency. Now the RMS is equal to 120 volts. The voltage is 120 volts. 4,44 times the number of turns is 200 times the frequency is 60, and you get that the flux maximum is equal to 0.00225 Webers. Now the B maximum is equal to flux maximum, which is equal to this, divided by the area. 20 centimeters square is 10 to the minus 4 meters squared. You have to transfer this in the basic unit, which is meters. The area is 20 times 10 to the minus 4 meters squared, and you get that this is equal to 1, 1.265 Teslas. So this is the amplitude of the magnetic flux density. So the expression for the flux density in the core is equal to this times sinus omega t, but omega is 2p60 times time. So this here is the expression for the magnetic flux density in the core. Now I have to obtain expression for the current in the coil. But now I'm just gonna remove all this except this expression for the flux density. I need space. Now for B, we have to obtain an expression for the current in the coil. Now, for the MMF, you know that is equal to H, the magnetic field intensity, times the mean length of the coil. Now, sorry. Now, when the coil, when the current is maximum, the magnetic field intensity is also has its own maximum value, and the expression for the current in the coil is equal to I maximum sinus omega t. But how are we going to measure what is the maximum length? Well, we know that the maximum magnetic flux density is equal to 1,1265, and you know that for this we have a formula that the Bmax is equal to the permeability times the magnetic field intensity, the magnetic field density, which is equal to H maximum. Now you get that the H maximum is equal to B maximum divided by mu, or the permeability of the material, and you get that the maximum field intensity is equal to 1,1265 divided by mu is equal the relative permeability times the permeability of the vacuum, and that is equal to 2500 times 4p 10 to the minus 7. And you get that the field intensity, maximum field intensity, is 358, or 0.575 ampere turns per meter. Okay, I don't need this anymore. Now we can measure what is the maximum current. That is equal to the maximum field intensity times the length of the magnetic field circuit, divided by n. 357 times the length is 100 centimeters, but 100 centimeters is 1 meter, so I don't need to write anything here. Divided by the number of turns, that is 200. We have 200 turns, and we get that the maximum current is 1,798. Oh, sorry, 793. Oh, too much decimals here. Amperes. So the maximum current is 1.79328 amperes. Then the current in this coil here is acting in this equation. So the maximum current is 1,79328 times sinus omega is 2p60 times t. So this is the expression for the current in the coil. Let me just see. Yeah, so thanks for watching, and in my next video I'm gonna do another example. So see you in my next video.